Alright folks, today we're going to talk about 4.6 exponential and logarithmic equations. We're going to start with a review of exponential and logarithmic functions and how we solve those special types of equations. So, exponential form means that you have something where you have a constant in the base, you have a variable in the exponent, and you have it equal to a y value. Now the key thing here is that your unknown is in the exponent. And so when we solve these, what we want to do is we want to use logarithms. And what we're going to do first is isolate the exponential, meaning we want our equation to look something like a to the x equals y. After we have that, we're going to rewrite our equation in log form, and that's going to look like log base a of y equals x. This will help us find our unknown. Now to find the value on the left-hand side here, we're going to need to use something called the change of base formula, or we'll type in log y over log a. You can also change it to the natural log and have natural log y over natural log a. Now, if we zip over here to the log form of an equation, we'll notice that we similarly have a base, and this time our unknown is in our log, or it's being logged, and then we'll set it equal to something we know. Now, in order to get the variable out of the log, we need to use exponentials. So our first goal is going to be to isolate our log so that we get something that looks like this. Once we have that, we're going to rewrite that in exponential form. So we'll have x equals a to the y. This gives us our unknown on one side and the things that we do know on the other. After that, you're going to solve for the unknown, and we'll show a couple examples of what that step might look like. All right, here we go. So, we're going to talk about solving exponential equations first, and we're going to go through 6 examples so you'll get a good flavor of all the different types of exponential equations that you might see. All right, so example number 1, pretty basic one. If we think about our 3 steps, our first goal is to make sure that we've isolated our exponent. And in this case, I have my base, I have my variable in the exponent, and it's set equal to something I know. And so what I'm going to do, since it's already isolated, I'm going to go ahead and rewrite it in log form. So we isolated it. Yes, it was. And now we're going to rewrite in log form. And that will give us log base 4 of 7 equals x. And in our last step, to solve for, x, we're going to use our change of base. And so x is going to equal log 7 divided by log 4. Or we could also use natural log of 7 divided by natural log of 4. Now, one thing you'll notice is on your calculator, when you type log, most of the time it opens up a parentheses for you. Now, the thing about that is you need to close that before you type in the division sign. So same thing, if I want to use natural log, it's going to open up a parentheses. I need to make sure I close that before I hit that division button. And when I type those in, this will give me about 1.404. So what we have here are two different types of answers, and maybe you've seen these kinds of questions on WebAssign. This one would be considered our exact solution, whereas this one is considered an approximate solution. So a lot of times, because we have a lot of decimals in our answers for exponential and logarithmic equations, we actually prefer to keep it in the exact form, but the approximate is not a bad way to kind of make sure that you've got the right number. Okay? So that's a pretty basic example, and we're going to take a look at another one that's pretty similar, but we're adding a few things. Namely, we're going to have to isolate our exponential before we do anything else. All right, so this time I notice that I have my base over here, and I have my variable in the exponent, but I've got a bunch of other stuff that I need to get rid of so that I can isolate my log. So, thing I'm going to do here, I'm going to subtract 200 from both sides. Let me zoom in a little bit. So subtract 200 minus 200. And that's going to give me 1/3 to the power of x equals 100. So that's what I mean when I say you need to isolate the exponential. Sometimes it's not all by itself like it was in example 1. We have to do a little bit of work. But now that we've got this, we have our variable in the unknown. We have 1/3 as our base, and we have it equal to 100. And so we're going to rewrite it in log form. So we'll get log base 1/3 of 100 equals x. And right here, this is your exact solution. Now, if you wanted to find out a decimal answer for this, you would use your change of base to type it into your calculator. And there's two ways you can do that. You can say that x equals log of 100 over log of 1/3. Or if you prefer the natural log, you could do natural log 100 over natural log 1/3. And same thing as the previous example, your calculator is going to open up that parentheses for you, so you need to make sure to close it. Otherwise, you're going to get a different decimal than I will. And same thing over here, open and close. And when we type that in, we should get about negative 4.192. And this would be considered our approximate answer. Okay, so we've got an exact solution and we've got an approximate solution. All right, let's take a look at a slightly different kind of example. So the next two are going to be examples where you have more than one base. So for example, I have a base on this side, which is 4. And I have the unknown in the exponent, 2x plus 3. But on the other side, I have a different base, 5. So 5 is not the same as 4. And I have a different unknown in my variable, or my exponent. So what I have to do here is I'm just going to log both sides, because like solving any equation, whatever I do to one side, I must do to the other. That will keep things equal. So I'm going to go ahead and use natural logs in this example, but in the next example, I'm going to go ahead and use the common log, okay? You can use either one, natural log or common log, and just so you get an idea, I'm going to show you one example of each, all right? So we've got our natural log and our common log. So in this case, I'm going to natural log both sides. So I'll get natural log of 4 to the 2x plus 3 equals natural log of 5 to the x minus 2. Now, if we think back to our log properties, anything that we have as an exponent comes down as a power. So what I really have here is 2x plus 3. And I'm going to recommend that you go ahead and put that in parentheses. So you bring the power down, 2x plus 3 times natural log of 4. And we're going to do the same thing on the other side where I bring that x minus 2 down. And I'm going to leave the natural log 5 where it is. Now, I know usually when we distribute, we actually have the thing we're distributing in the front, but we can actually do that same thing here. I'm going to distribute that natural log 4 to the first term and the second term. And on the other side, I'm going to distribute the natural log here and here. And so what that's going to give me is 2x natural log 4 plus 3 natural log 4 equals x natural log 5 minus 2 natural log 5. Now from here, this is probably going to be our messiest step. Things get a lot better after this. And what we want to do now is we want to collect terms that are like terms. And so what I notice is this term has an x, and so does this one. So I'm going to move them to the same side. And I also notice that this term does not have an x, and neither does this one, so I'm going to move those to the same side. So when I do that, I get 2x natural log 4 minus x natural log 5 equals negative 2 natural log 5 minus 3 natural log 4. Now the nice thing about getting these terms on the same side is that they both have an x, and so I'm going to go ahead and factor out that x. So x, parentheses, what's left? 2 natural log 4 minus natural log 5 equals negative 2 natural log 5 minus 3 natural log 4. And the only step I have to get x by itself is to take this, divide it over to the other side. So I've got x equals negative 2 natural log 5 minus 3 natural log 4 over 2 natural log 4 minus natural log 5. And as messy as this looks, this is our exact solution. Okay, that is our exact solution. Now, if you want to type it into and turn it into a decimal, I believe that you will get around 6.343, and that would be your approximate solution. So on an exam, it's totally fine to leave it as an exact. In fact, that actually shows me that you really understand the process. And an approximation, I think sometimes WebAssign asks for that, so it's nice to know how to turn it into a decimal as well. Okay? So again, this was a question where we had two different bases on two different sides, and we were able to natural log both sides. But we could have done the same thing with the common log, or whenever that base is 10, and that's what I'm going to show you in the next example. So over here, I'm going to go ahead and write that I'm going to be using the common log for this one. Okay? And if I can think about how this one compares to the other one, I've got a base on this side, which is 2. Got a base on this side. They're different. One is 2, one is 5. And I've got this exponent, which has my variable, and I have this exponent, which has my variable. And so I need to get those variables out of the exponent. So I'm going to go ahead and common log both sides. So that's going to look like log of 2 to the 2x minus 3 equals log of 5 to the x minus 2. Now, just like last time, those things that are in the power, I can bring them down to the front like a coefficient. So here, I'm going to have 2x minus 3 log 2. And on this side, I'll have x minus 2 log 5. All right, so like last time, I'm going to go ahead and distribute. I'm going to make things a little messier before it gets better. We've got 2x log 2 minus 3 log 2 equals x log 5 minus 2 log 5. And again, I notice that I've got some terms, in fact 2 of them, that have an x, so I'm going to move them to one side. And I have 2 terms that don't have an x, and so I'm going to move those to the same side. So on the left-hand side, I'm going to get 2x log 2 minus x log 5, and that's going to equal 3 log 2 minus 2 log 5. And just like in example number 3, I notice that both of these terms on the left-hand side have an x. So I'm going to go ahead and factor out that x, and that'll leave me with 2 log 2 minus log 5 equals 3 log 2 minus 2 log 5. And my last step is to take this, divide it to the other side to get my exact solution. Log 2 minus log 5. And this, again, is the exact solution. Now, if you want to turn that into a decimal, use your calculators, and you should get an answer of about 5.106 for your approximate solution, okay? Now, don't forget that calculator puts in a lot of parentheses, so you want to make sure you close all the parentheses that they put in, okay? All right, so let's go ahead and move on to our last 2 examples of solving exponential equations. All right, so these 2 actually involve our knowledge of quadratic equations. Okay, so knowing how to factor, knowing how to use the quadratic formula are definitely really important, even when we talk about other kinds of functions. All right, so we're going to start off by going ahead and doing something to both sides of the equation. And what that something is we're going to take the whole equation and we're going to multiply it by 3 to the power of x. And so when I do that, I'm going to get 3 times 3 to the x times 3 to the x plus 9 times 3 to the x times 3 to the negative x equals 28 times 3 to the x. And so all I did was take that pink 3 to the x and I multiplied it to the first term, the second term, and the third term. All right, now I'm going to use some rules of exponents that hopefully I remember. Well, I remember. Hopefully you remember too. So this first term here is going to become 3 times 3 to the x squared. plus the second term is going to become 9, 3 to the x minus x, which equals 28 times 3 to the x. Now normally I'm going to skip this step and I'm just going to go straight to 3 to the 0, and more significantly I'm going to go straight to 1. Okay, so off to the side, let me just write that out. 3 to the x minus x equals 3 to the 0, and 3 to the 0 equals 1. So this whole thing I can write as 1. Alright, so I'm going to do a few things here. I'm going to rewrite this with a 1, and I'm going to take this term and move it to the other side. So I've got 3 times 3 to the x squared minus 28, 3 to the x, plus 9 equals, what's left on that right-hand side is 0. And now I'm going to do a little substitution. So everywhere I see a 3 to the x, I'm going to replace that with a u. And so that's going to look like 3u squared minus 28u plus 9 equals 0. And let me just go back and highlight for you, this 3 to the x became that u, and this 3 to the x became that u. Alright, now, as promised, we're going to go back to those quadratic equations. So I have a quadratic equation here, and I'm going to go ahead and see if it's factorable. So 3u and u is how I'm going to get 3u squared. And if I put a 9 here, that's going to give me 27. And if I put a 1 here, that's going to give me 1. So 27 minus 1 will give me this negative 28. Nice, it's factorable. All right, so we've got 3u minus 1 equals 0, and u minus 9 equals 0. And so in this case, we'll get u equals 1/3, and in this case, we'll get u equals 9. Now, a lot of times students stop here and they're like, yes, I'm done. But what we need to do is we need to make sure that we sub back in, not u, but 3 to the x, because I don't want to find u, I want to find x. So this question really is 3 to the x equals 1/3, and this question is really 3 to the x equals 9. And if you remember your exponents, 3 to the x, 1/3 is really 3 to the negative 1. So I could say x equals negative 1. And over here, 3 to the x is really 3 squared, and that makes x equal to 2. All right. Kind of a complicated example, but we're going to go ahead and try one more like it just to make sure we've really got it. And also to check out what happens if it's not factorable, okay? So, example number 6. 2 to the x minus 6, 2 to the negative x equals 6. And so I'm going to go ahead and do the same thing that I did on the last problem. And I'm going to go ahead and multiply everything by 2 to the x. And so that's going to give me 2 to the x times 2 to the x minus 6 times 2 to the x, 2 to the negative x equals 6, 2 to the x. And let's just go ahead and highlight this 2 to the x was that pink one. This 2 to the x is the other pink one, and this 2 to the x is when I distribute it to that last term. Okay, So this term I can actually write as 2 to the x squared because I'm multiplying it by itself. And these two are going to give me a fancy way of saying 1. So I'll get minus 6 equals 6 times 2 to the x. And I'm going to go ahead and do that u substitution again. I'm going to let u equal 2 to the x this time. And so what that's going to give me is u squared minus 6 equals 6u. And again, that comes from this 2x squared became u squared. And this 6 times 2 to the x gave me 6 times u. Now I notice that I've got a quadratic here, and so I'm going to move everything to one side and set it equal to 0, because that's a good strategy to use anytime we're using quadratic. And I notice this time that it's not factorable, so I'm going to need to use the quadratic formula. All right, so let's bring that all the way up here. I've got x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And let's go back to our quadratic and determine our a, in this case, is 1, our b is negative 6, and our c is also negative 6. And so when we plug that into our quadratic equation, I'm going to get a positive 6 plus or minus 36 plus 46. Oh, not 46. I meant 24. Sorry. Oh. Plus 24 all over 2. So 6 plus or minus the square root of 36 plus 24 is going to give me 60 over 2. And you can turn that into your decimals to get your approximate solution. So 6 plus the square root of 60. And then I divide it by 2 is going to give me about 6.873. And if I do 6 minus the square root of 60, and then I divide it by 2, I'm going to get negative 0.873. Okay. So when I have these values, I want to keep in mind that I'm not done yet, because this is what u equals. This is not what x equals. So I need to do 2 to the x equals 6.873, and 2 to the x equals negative 0.873. And when I do that, I can solve it just like a regular log equation. Go back to example 1 or example 2, and you should get that this is going to be 2.781, and this one is going to be, when you try and type that into your calculator, you should get an error. It should tell you that it's undefined. Okay? Now this is going to happen from time to time, which is why it's important that we check our answers. So in this case, this second answer is not actually an answer. And we really only have one solution for this equation, okay? So make sure that you check that when you type in your work that you're getting an answer from your calculator. If you get an error, it just means that that wasn't actually an answer. Okay? We're going to pause here, and in part 2 of the video, I will talk about how to solve log equations.